All right, welcome everyone. You can go to the next slide, Fraser. So I'm Megan Lewis. I'm the program director for the Carbon Leadership Forum. I'm really excited to welcome you today to the webinar focusing on material efficiency for embodied carbon reductions. I'm joined today by Francis Yang, Fraser Reed, and Mike Greniak, who, in addition to their decades of experience as structural engineers, are also three of the key contributors to the SE2050 challenge. If you go to our commitment, um, a little bit of a history of CLF with SE2050 and why we're particularly excited about partnering with them on this webinar today. SE2050 started back in 2016 as just a working group within CLF, which became another working group within ASCE. And then in 2019, CLF officially issued the SE2050 challenge. And the SEI Board of Governors accepted that challenge in April 2020, leading to the final public launch in November 2020. So it was a little bit of a journey there. And it's just been so impressive to see the work that you'll hear a bit more about today in terms of resources and other work that they've been doing since then. If you go to the next slide. Today, what we want to focus on is material efficiency, sometimes called material optimization. We spend a lot of time at CLF and just when we talk about embodied carbon and generally on how we can use better materials. And today we're really going to be focusing on what it looks like to use less materials, focusing on structural systems and buildings. And so you can see this little diagram here. You've probably seen a lot of versions of this, of the earlier in design that you start, the bigger the opportunity for reductions. And you often see structural system efficiencies. That's what we're here to talk about, to get beyond just saying we can use less by designing better, to understand a little bit more about what that actually means. So with that, we have a lot of content today, so I'm going to pass it over. And hopefully we'll have a little bit of time for questions at the end. So thanks.
Great. Thank you, Megan. Yeah, we're really excited that when CLF reached out to talk about this, because we feel like there it's like we see it in a lot of lists, right? Like strategies to reduce embodied carbon, but not much detail beyond that. And so this is, we think, the start of some dialogue about it. There's a lot to unpack here. Actually, preparing for this presentation, we had to take out a lot of content. So we're just hoping that this is the beginning. Okay, well, let's start with some definitions. This is courtesy ChatGPT, but we're talking about optimization and the use of materials, minimizing waste, which is helping to reduce resource consumption, but with keeping in mind that we have to still maximize the functional or the structural performance of a project, and it has all these good benefits. But next picture. But it's I think when we think about lower carbon materials, that's really focused on the materials themselves and how they're made. But when we talk about material efficiency, we're also addressing the resource use and recognizing that there is a finite amount of materials. Some the materials already used in construction are already coming under stress. This is a neat diagram, I thought, that actually gives a timeline and comparison from the New Scientist, just kind of illustrating that idea of we need to treasure our materials and use them more conscientiously. And then here are some really high level estimates and some pretty comprehensive or deep dive studies that are out there. So from International Energy Agency, one of the global authorities on energy use, they did a study a few years ago, actually, that identified that for steel, cement, and aluminum, that there could be approximately a 30% savings if we could just use materials more efficiently. This isn't limited to construction, because steel and aluminum are used in a lot of other things, but it was alarming to me when I first saw it that they put the number that high. And then there's these other sources, noting some other ranges and percentages of how much how much overuse in material really that is in our current designs. Okay, next. And here's just kind of one of those particular studies that went into a little more detail on identifying the, you know, the origins of that overuse. A good part of this is kind of just baked into our practice, in engineering. A portion is risk mitigation. So there's reasons for this and good reasons. And another 20% from kind of the simplification that we have started to do to reduce the effort, in design, and design involves a lot of iterations and design changes that we need to carry on and update throughout the project. So reducing that effort, if we can make things more, uh, uh, standardized or the same, and then reducing construction errors too, right? If there's fewer unique things, so, and that's what we call rationalization. But it's this trend though of doing that, and then like safety factors and just like more and more layers of risk and simplification have just led to quite a large margin between what we really need and what we end up with. And then this is just highlighting some of the ideas from policy. So just making that link here. Again, what Megan was saying, that where using lower carbon materials has led to material GWP limits, which we often find in like bike lane and those types of policy mechanisms, using less material. Right now, the only kind of mechanism we have in the US is with whole building LCA, and which we can find showing up just more recently in policy, like in CalGreen. And then if you want to say, well, LEED has the whole building LCA credit, and there are some jurisdictions that or like some projects where you're required to get LEED, then that can come into play. But what we just wanted to point out here is that whole building LCA is written right now so that you're reducing from a baseline, right? And that's on the right side, that you're showing a certain percent reduction from a baseline, which is it's great, but it's often using the material GWP limits approach, where you're comparing your project lower carbon materials to a baseline or industry average equivalent of that material. But you could be using a lot of like material, like not being super efficient with the materials, and have a really high, or just that the project is employing a lot more materials than kind of, maybe, there could be really good reasons why that your project needs to have really high material use. But if just, if it's not kept in check or kind of challenged, you could end up with something that's overall still really high compared to what this concept of a project GWP limit, which is a trend we're starting to see overseas with that'll is meant to also rein in the material use. So next, an example of that is the UK net zero building standard that it's just in draft right now, or pilot. But introducing to their region this idea of like, can we start to set some project carbon intensity limits, and then ratchet those down year by year until we get to zero by 2050. And then this one example that we found too in rating systems, which are more voluntary, because there is this tension too, like how it can be really hard for policymakers to try to enforce material efficiency. So maybe kind of starting off with them in the more voluntary realm in green building rating systems would be like the first step. Singapore Green Mark, they have a rating system that actually has this particularly about the concrete use in a building, and they're doing this through this thing called the Concrete Usage Index. or you can get points for, yeah, this calculation. So yeah, so these are just some examples. This is like example of how that's calculated. And next, and what would this actually look like? Like what would pushing towards more efficient use of materials look like? Just wanted to give a couple of ideas here too. And this is a study that Arab did, and we're comparing a flat slab and calling that, you know, one of the most popular systems, concrete systems, and then pushing towards the most efficient kinds of slabs we've seen, where, you know, you're just having material where the highest load is, and then following the load path, and so that just putting material where the stress is. Then the taking those concepts, like we laid out a whole bunch of slabs that were designed to the same design criteria, including serviceability and fire, all of those parameters. And if you say flat slab is unity, what we found is that the most efficient system we could possibly think of would be like you know, that's only a third of the use of so 0.33 compared to 1. That's saving almost well, it's saving 2/3, right? 2/3 of the material, the concrete. And then on the steel side, we were also part of this project where the geometry of the steel, we were just given like so much freedom and allowed to optimize the you know, the steel members to a point where they were able to drive the steel tonnage down drastically. And then we just kind of pulled up some of our other airport projects alongside it, where the geometry was just kind of, you know, the architect kind of said it's going to look like this, and we like have to design your structure to this. So to achieve these really long spans, but then have the freedom of the form following function, you know, and efficiency, it, you know, drastically reduced the steel tonnage. And I think that the lesson learned here was just the collaboration that we were able to have in this project with the architect and be part of, you know, determining that geometry and letting efficiency inform that a lot. So these are just a couple examples, but Fraser is now going to go into a lot more about the strategies and what you can actually do in design and on your day-to-day projects using SE 2050's resources.
Thanks, Francis. So SE2050 provides a lot of resources on the website. So here's a bunch of the content that's provided for structural engineers. It's a two-way commitment, really. So there's expectations for signatory firms to submit data, etc. But SE2050 provides resources to support those signatories. So a few things to highlight here: the ECIDs, embodied carbon intensity diagrams, the ECOM tool, which is order of magnitude, embodied carbon order of magnitude for high level decisions, and then the design guidance page, which is specifically focused on improving material efficiency and reducing embodied carbon through design. So this is the design guidance page. So the intent is, as I mentioned, providing guidance for improving material efficiency. The page is really mostly written content. I also have it pulled up just to show you with sort of expandable menus. So there's lots and lots of content on the design guidance page, and then it provides reference content with lots more useful links if there's a particular topic that is relevant to you. The guidance is organized generally by timeline, so start to finish of a project. So basically highlighting that some of the most significant impact can be made during the early design stages. But as you progress through a project, then your decisions become more and more refined. So the guidance is laid out in that way. Everyone should be kind of generally familiar with how embodied carbon is calculated, but it's basically quantities of building materials multiplied by GWP per unit. And the reason I brought this up is just to highlight um, on the resources page, SE2050 provides design guidance, but also specification guidance. So design guidance, you can think of meaning, focused on reducing the amount of stuff we're using in design, and then specification guidance focused on reducing the carbon intensity of the stuff that we're using. And so I don't have time to cover all of the design guidance content. That would be its own webinar. So the purpose just of the next sort of 10 minutes here is just to highlight some of the key sections and give some specific design guidance pointers that might be useful to you. But please visit the website. I saw someone just paste the link in the chat, so please visit the design guidance page for more info. Um, Before we get into that, the kind of hierarchy for reducing embodied carbon in structural design, this is an I-struct-E diagram, but there's probably an analogy here that everyone should be familiar with in terms of how we treat our waste, the reduce, reuse, recycle analogy, and it's the same for structure in the sense that reducing the demand for the amount of new stuff is really the first step to reducing embodied carbon. Another analogy that would be similar is with operational carbon, reducing energy demand before you slap solar panels on your roof and do jazzy ways to generate the energy more efficiently. So for structures, reduce demand, reduce the amount of stuff you need before you focus on how to make the stuff as efficiently as you can from a carbon standpoint. And then even within that, there's a hierarchy. So focus on building less and from a consultant standpoint, and then how you build appropriate structural configurations and criteria, and then focus on building what you have to build, building it as efficiently as you can, and then you get into minimizing waste and low carbon materials. This is highlighted earlier on Megan's slide, but this is just describing the time-dependent nature of decisions, and I mentioned it before as well, but the most impactful time of a project is during the early stages. That's when many of the big decisions get made that are difficult to reverse as the design progresses. So really recognizing that and where you have influence early on during a project. Next is identifying the big ticket items or where the big wins are, where you can have the most impact. In order to do that, you need to understand where the embodied carbon is coming from. So this will vary from project to project, but for the most part, roughly half of the embodied carbon in structural systems is in the floor systems. So start there. Also, foundation systems in structures are typically very carbon intensive. You can't always do as much with your foundation systems, but the point is identifying where the big wins are will allow you to have the biggest impact. And different types of buildings, if you have a tall building, then your lateral system might be another good area to target. So understanding that early will allow you to be targeted. This slide really illustrates it's really not a one size fits all. Once you've identified your big ticket items, you'll have a better understanding of where to target. But it's not just one thing that you can focus on that's going to be applicable everywhere. Really, it's kind of a mixture of different things, and this is why there's so much content in the design guidance page as well. So start by optimizing loadings, focus on reducing your spans, finding efficient grids, etc. Optimize your serviceability criteria, consider different materials and use them efficiently, and then focus on material specifications. And the recipe of all of these together will allow you to optimize your design and reduce carbon. Focusing on floor-based studies early on in the project. As I highlighted earlier, floor systems are typically the largest contributor to embodied carbon of the superstructure. So it's therefore typically a good area to focus on. Identifying optimal systems and using this to or use regular structural grids and coordinate those grids with your design team. Doing so can result in dramatic savings. As a general rule, shorter span structures are generally lower carbon. What this chart is showing you is that it's not a straight line. This is based on a tool that we developed. It's GWP based on different systems for span dimension, and you can see the curve. It's kind of exponential with longer spans. Your structure really, embodied carbon intensity really begins to escalate. Try to avoid irregular grids and excessively long spans and cantilevers where possible. Focus on your loading criteria. So typically higher loading is more structure and higher embodied carbon. So obviously codes are there for a reason and prescriptive when it comes to minimum design loading. Use the minimum design loading prescribed by code. That's typically live loading criteria, but often we see on projects custom loading criteria introduced. And the message here is really to interrogate those criteria and work with your client so they understand the impact of those criteria on the design and on the embodied carbon of the building. Live load reduction, utilize it. It's there for a reason. Probability of multiple floors being loaded goes down and down as tributary increases. So make sure to use those provisions. Skipping around, but coordinate your superimposed dead load assumptions. If you're making assumptions, be sure to coordinate those with the actual design to avoid being conservative. And then some other recommendations here. So in a similar vein, serviceability criteria. In many cases, service will control the design. So make sure to take advantage of higher deflection limits. You know, for roof structures, for instance, roof structures can deflect more, and occupants still be comfortable. So make sure to be aware of those and to use those and interrogate atypical deflection limits. So if you believe there is a facade deflection criteria, make sure that you fully understand what that criteria is and you're applying it correctly, for instance. Vibration design is a bit of a dark art, but really it's important to interrogate the criteria and communicate the impact of these criteria and to refine them in order to highlight the carbon impact of vibration criteria. You can consider dampening as well as an alternative to stiffening your structure. That will generally be a more carbon efficient approach. I won't dwell on this a huge amount because it's Francis was highlighting this earlier in terms of compounding safety factors and rationalization instead of optimization, the impact of that, and if looking at real structures that can lead to utilization that is well below 100%, sometimes as low as 50% in structures. So be aware of compounding safety factors and avoid rationalization methods, especially nowadays where computational tools allow us to approach design in a time efficient way that also allows optimization of structural elements. So use the tools that are available to you. And some various optimization methods here. you can read on the design guidance website for more info. Just a brief slide for kind of our most common structural materials, but on structural steel, work with your fabricator. They're typically they typically want to work with designers to optimize the design and get the balance right with constructability and reduced embodied carbon. Higher strength steel is available if you have strength controlled column truss members. Use higher strength steel. You can reduce your embodied carbon. Utilize camber. It's there for it's done for good reason, and it typically will allow you to reduce weight. So utilize that, and then consider different shapes and joists and castellated beams that take the weight out of steel structures where it's not contributing a huge amount. Similar vein, concrete. Not all concrete is made equal, so consider your concrete strength and mix selection, because the variation in embodied carbon can be really significant within different mixes. And then focus on concrete's a heavy material. So focus on reducing the weight and mass of your structural system so that your self-weight is not controlling your structural design. So different ways of doing that with different merits and pros and cons, but ribbed and joist and waffle slab systems basically put the amount of concrete towards the outer part of the structural section where it's doing the most work. Similarly, with voided slab construction, that's bubble deck does the same thing. And then post-tensioning will generally allow you to cut mass out of your concrete system and embodied carbon, and same thing with pre-stressed and hollow core. Consider also high strength reinforcement. It's available and will allow you to reduce the quantity of reinforcement for strength controlled concrete sections. For wood, similar to steel, involve your fabricator. They're generally there to help, and aim for material efficiency regardless of sequestration. So never take, when you're looking at how much material to use, if you account for sequestered carbon, it can encourage more material consumption. Always aim for less. And then efficient wood systems as they relate to material use and material intensity, similar to steel and concrete truss and truss systems, and various different wood sections allow you to be as efficient as you can with material consumption. A brief statement on composite and hybrid floor systems, but really use the right material for the right job, and identify, with floor systems, with steel frame construction, typically a lot of the embodied carbon is in the concrete deck. So AISC has published a steel timber hybrid design guide to give designers, resources to integrate timber hybrid options. So just use the right material for the right job and consider all the options. So I just have one project example here, a Björhappold example. This is a real project. I think when we talk about reducing embodied carbon in design, often we get, the initial feedback or expectation is, oh, we're going to have to do a timber building, and that's really not the message here. This particular project was a concrete building in Tempe, next to Phoenix. It was, concrete was the most readily available material. It was what the contractor and owner wanted. So we knew we were designing in concrete. So on most projects, there are similar kind of push and pull in terms of material selection, and you can be efficient or you can address material efficiency within any structural system. So lots of exposed concrete on this project. You can get away with that in Arizona without significantly changing energy performance. But this particular project was it's a good story because we worked really hard to address this. This was also kind of 5 years ago before we were actively kind of measuring and comparing embodied carbon in at the same rate as we are now on projects. But we identified that basically the majority of the embodied carbon of the structure was going to be in the floor system. And this was the first use of voided slab in Arizona. We also used high SCMs in the concrete, specifically fly ash, because that's what was locally available. This is just really the reason I included this slide is just to illustrate that each wing of the building was kind of different span conditions and performing differently. The north wing was a shorter span dimension. That's where all the vibration sensitive equipment was expected to be in this building. We presented comparison for flat slab versus voided slab for each wing of the building. Ultimately, it was used in the south wing where the span condition was longest. And working with the contractor on that, we were able to present a cost and embodied carbon reduction by using the voided slab in the longest span wing of the building, which is where the building bridges over this historic canal. Also, when you do this and really get buy-in from your contractor, from your owner, you can generate some excitement around this. So using the first voided slab in Arizona, they kind of really went to town and branded it, and the owner really got behind it. And just a final summary slide of kind of embodied carbon reduction from this project. We had these kind of two key interventions. One was the voided slab, and one was the high fly ash concrete. Contribution of floor slabs was 64% to total embodied carbon here, which is really a telling story. And then interestingly, using the fly ash concrete reduced about 30%, whereas the voided slab was about 9% here. So interesting reflection for us in terms of how the impact of our interventions. Okay, I'm going to hand over to Mike, who's going to talk a little bit about taxonomy.
Thank you, Fraser. That was fantastic stuff. A lot of really good opportunities there. So I'd like to start by taking that information and moving it into how can we talk about our material quantities that is a little bit more meaningful, consistent, and collaborative than it is today. I think it's fairly safe to say that we're all aware that we very much need these benchmarks, these baselines, and ultimately these appropriate reduction targets. But I fear that need is slightly outpacing the emphasis we're putting on reviewing and organizing our structural material quantities in a meaningful way. Francis mentioned policy and potentially setting carbon intensity limits. And Fraser, of course, you mentioned using less material is the number one on the list, the hierarchy list of reducing embodied carbon of structural systems. The problem is we're not collecting material quantities and we're not talking about material efficiency. Okay, so if we can go to the next slide, Fraser, please, which is this slide. And I really like this example because the plot on the right is an example of 3 life sciences projects, okay? And these are the embodied carbon of the structural system, and they vary for different reasons. But, in our current methodology of collecting this information, we really don't know why it's varying that much. At best, sometimes we break things up between the superstructure and the substructure or foundation. But let's say in this example that the impact of the foundations was exactly the same for each one. Okay, we're severely limited in what we can do in terms of a detailed analysis because there's no breakdown of the different structural categories within that GWP number. There's also sort of a problem here because there is no link between the material quantities that we're using and the embodied carbon that's reporting. Okay, so we really have no idea right now how efficient our systems are. All this great work that Fraser and Francis talked about are not showing up or represented in our current methodology of reporting this information. And we certainly don't know how efficient each one of these projects is just looking at the GWP numbers. And then I would say one of the biggest challenges we're having is that we're not making any sort of rational connections between the materials that we're using and the embodied carbon of these systems. And I think the next slide, Fraser, sort of highlights this. This is an example of looking at the material efficiency. This is using our ecom tool, which is one of the great resources that Fraser is pointing you to on our website. And this is designing a typical composite concrete steel floor framing system. So that would be materials of steel, concrete, and concrete reinforcement. So on the left, it's got an embodied carbon of about 130 kilograms of CO2 per square meter. And that's using 35 tons of steel and 185 cubic yards of concrete. If you do that same system and you design it somewhat less efficiently, but you go ahead and you're really excited because you got a lower embodied carbon concrete on the topping slab, yes, you can get a slight reduction in the overall embodied carbon, but you've also used 30% more structural steel. Okay. And so one thing that's happening now is in our profession, we're really focusing on that 2% gain. We're really excited about that. But if we dug into those numbers a little bit more, we'd probably want to understand, well, wait a second. So you actually use 30% more steel, and even if you did know that, you don't know where that steel is located. Okay. So it makes it really, really difficult to make any sort of material efficiency comparisons between these two systems. Next slide. So you've got these great firms out there, and like Burrow Happold, and this is a slide that Fraser just showed, and it's fantastic, right? So his company on this project broke down all of the embodied carbon by the structure component type, which is fantastic. Okay, the challenge. And I think Fraser would even admit this, and other firms would admit it, is that there is a variability in how we're categorizing all of these components. Okay, so your columns, your beams, and your slabs may be categorized in different ways, not just regionally or nationally, but even within their own office or across offices of the same company. Okay, and so that makes any sort of comparisons really challenging, if not in our current state of practice, almost not super useful. Okay, or at least fraught with errors. Okay, so one thing that we need to do is we need to follow our boy Carl's lead here. So I joke, but this gentleman apparently in the 1700s was a well-known figure who, at the time in the 1700s, there was a lot of confusion about how to talk about the different parts of human things, and so he developed this taxonomy, which basically created a standardized framework for communicating and studying the human body. And so, just like he did in the 1700s, we're sort of in that place when it comes to categorizing our buildings. And what's really interesting is if we just go back real quick here, so Fraser, is that some of this has nothing to do with sustainability. Okay, I received estimates from two contractors this morning on the same project, and they both categorized their materials in different ways, and we're not following any sort of standardized system, and it has nothing to do with sustainability. Okay, so this is, we're playing catch up here, and we're trying to apply a system that doesn't necessarily exist to the desperate needs of our current sustainability push here. So on the next slide, one of the we have several different goals and sort of the rationale for developing this taxonomy. Number one, and Francis alluded to this, is connecting the functional class or the functional service of a particular component with the material and the embodied carbon. Okay, this opens up several different things. Number one, it could allow us to back check the embodied carbon numbers. I like to think as a structural engineer, I really understand because over time and experience, I understand how much embodied carbon, or excuse me, how much material quantities are used in a particular system or loading condition. But I really don't have that innate ability yet on the carbon side. So at the very least, having the material quantities allows us to back check some of the embodied carbon numbers. And I think we all know that the embodied carbon impact factors are varying over time. Okay, it literally every 6 months, every year, right? You could potentially get a new number. And so, one of the ways that this could improve carbon tracking is simply by having those material quantities that could be paired with different GWP impact factors over time. Other things we want to do is simply by forcing us to produce this information of material quantities by structural component. In theory, a structural engineer may be more compelled to examine their design because it's omnipresent, it's in front of them, and they may identify worthwhile adjustments that could be done using some of the things that Fraser talked about. I will tell you, I've been a practicing structural engineer for 25 years, and I sense, and I clearly can't speak for all firms, but it is not omnipresent in a firm to constantly talk about material efficiency. At least, I don't want to speak for all firms, but that's the feeling I get. And so it's very, very important to start showing this information, start understanding it on our projects. And then I would say one of the biggest challenges is that we need to have a consistent methodology so that we can collaborate office to office, region to region, across the country, internationally. And so these are sort of our rationale and some of our goals associated with the taxonomy. On our actual taxonomy, the approach we're taking is a bit of a hybrid approach. Fraser, if you, yeah. So this is the summary of the proposed taxonomy that we're going to be publishing soon. This is just a snapshot. And so what we elected to do was take OmniClass Table 21, which is an established classification system that has generally broad support in the AEC industry, but it doesn't have a lot of granularity, and pair it with a structural component taxonomy that we developed off to the side that has a lot of granularity, but it's a very standalone item. And so our idea is that we've mapped these two systems together, and that will satisfy all of those points that we talked about, including the collaboration and being able to speak the same language, but also giving enough granularity such that a structural engineer follows the logic a little bit more than maybe in some of these classification systems that exist there today. There's a lot behind this slide, which could be its own presentation. I will say we studied many different classification systems that are based both here in the US, in the UK, Australia, Europe, Japan. I mean, we looked at a lot of different systems, and we also balanced what's out there with what is happening at AIA DDX, at the ECHO project, Athena, what does Tally do? All of these different sort of platforms that exist out there or initiatives, what would be the best? And we landed on OmniClass Table 21, and it's not perfect, but we've done the best we can to sort of link the two. And we went through a whole series of mapping exercises. And so what you see on your screen here is on the left is the 4 levels of OmniClass Table 21 just for the shell. And everything on the right of those red lines is our individual taxonomy. And so we literally took as many buildings as we could think of, building types, and broke them down to their component parts, and then tried to map those to the OmniClass tables. It's a very arduous, sort of labor-intensive process. And there's several things that we learned. We're not using all categories. We're not mapping to fire escapes or ladders. The fact that these OmniClass, they really push for roof and floor structure to be separated. So we went with that, but that required us to add additional layers to ensure the accurate mapping. Bearing walls and shear walls was very frankly annoying because the only place that OmniClass has walls is in the interiors. And so shear walls and bearing walls fall under interiors, which is not something you'd normally think about. On the substructure, next slide. A lot of other challenges here. I would say of particular note is learning that foundation systems are talked about in very different ways across the country. Okay, I always think of those big slabs below concrete cores as mat slabs, mat foundations. A lot of other people think of them as raft foundations. And so just learning about the different language, how even structural engineering colleagues talk about things was quite interesting. And then on the foundation side, it was very awkward because we had to start skipping levels. We mapped directly from ours to level 3 instead of level 4. And so I just wanted to give you a flavor of the effort that went in to this. And so the taxonomy looks like next slide, which you can't read, which is done on purpose because it's not finalized. But in effect, we're going to get into the next stages, which is, we're testing this, we're evaluating, we're updating it, we're going to publish and then distribute it. And then, of course, we'd love for you to use it and provide us feedback. So I want to thank you for your time and got a little flavor of what's going on there. And on the final thoughts, I think before we get into the discussion session, I just want to say, you've seen a lot. We've thrown a lot at you. We would say don't necessarily feel the need to do everything or have the most extreme push to make changes on your projects. Even little things make big differences. I always use the example of looking at your typical details, and you probably don't need that full height welded stiffener plate on those beams. Identifying the big ticket items. I think what Fraser said really nailed really hit it on the mark there. And looking at your slabs, small changes to your slabs can make huge differences across your projects, given all the embodied carbon is there. Engineers, structural engineers, I think are the most amazing people on the planet, and so as a result, we're always balancing different things. I hope the structural engineers are called like that. We have to balance many different things: life safety, serviceability, embodied carbon, owner satisfaction. There's a lot of things that we have to balance, and so we are certainly more than capable of it. And then I think it's important to sort of be a pest, and you can leverage the discussion of material efficiency to enable you to talk about embodied carbon earlier in the project. Okay, a lot of engineers struggle with bringing up embodied carbon early in the project, but if you put it in the guise of material efficiency, you can link material efficiency to cost, and you will certainly get a lot more attention earlier on in the project than saying that you want to use Sublime in all your concrete. And then again, culture change. I think behavior change and the role of the structural engineer and the architect and that partnership is pretty important. And so I think with that, I want to sort of move on so we can have a little bit of discussion time. And I'm going to hand it off to Megan. And I just want to, for Fraser and Francis, thank you very much for your time. And we'd be happy to move on to the next step here.
Thanks, Mike. Thanks to all three. Those were fantastic presentations. We have a few questions, and then I'm also going to be taking a look at the chat. And so if you have burning questions, please do, and then I can read them off to the presenters. So I think for the first question we had was, what do you think the biggest barriers are to designing for maximum efficiency in practice today? So Francis, maybe start with you, unless one of you is burning to answer first.
I think that I think it comes back to the just changing from what we normally do. But I think that we start to kind of look at this more incrementally. Like I love in the chat, like the okay to be a pest. It's I don't think we're trying to present all of this as like it's only if you try all of these things that you're even trying something to improve your material efficiency in your project. It's like identifying and bringing the question up even once and just starting to nudge, I think is going to be really cool.
It sounds like culture change being a big one of just starting. starting the path being a big barrier. What about you, Fraser? And also, we can probably hide it so we can see each other's faces better if you want to stop sharing.
Yeah, I was just going to add, back to the time dependency on carbon and making the big decisions early. I think one barrier I see is, you know, wanting to get too detailed in your embodied carbon measurement early on in a project when really what you should be doing is order of magnitude comparisons and trying to influence those big decisions early. So, does the building need a basement? Basements are typically very carbon intensive because of the amount of concrete. Or what is the right structural depth for the spans that you have, and are those spans flexible, and having those big decisions early, because when you progress into DD and beyond, it's typically those things get locked in and you can't really backtrack. So that to me is a barrier, and recognizing where you have influence at the right stage of the project.
Mike, do you want to add anything?
For me, I think it's important to embrace the pain of behavior change, and being being a little bit more proactive where you can. Okay, I like what Francis said about incremental changes, but you've got to do it, and you've got to be okay with it being a little bit painful. And when I say painful, I just mean it could be a little frustrating. It might not go as fast as you want. A lot of people might say no to you for a while, but you've got to just sort of embrace that, and it's just part of the process. So that's all I would add on the non-technical side of things.
Megan, if I could actually, the barriers like that just kind of struck something else in my mind. I think we trended toward this, like in that whole study of, flat slab being the most popular now. It wasn't at a time period in time, right? Like waffle slabs were actually pretty popular, even two-way beam column. Like, so things that are more efficient, trusses, but material costs have gone down relative to labor costs. And I think that's been one of the drivers. But ultimately, I feel like the barrier is that materials now aren't valued as much as they should be. Like the cost of materials isn't actually reflecting their true cost. So, I mean, that's like something that's really hard for an structural engineer to change. But I just wanted to highlight that as a barrier.
Okay, I'm looking at some of the ones in the. Well, I think it sort of builds off. So one of the questions from Luke is Francis wanting to hear more about how you approach collaboration with the architect as well as the contractor for material optimization. So the example of the Nervi slab, where it seems like a great place to make a cost case, but there may be sensitivity in terms of architectural expression.
Yeah, that was a desktop study, Luke. Sorry, we didn't actually get to do that on a project. We are seeing though. Philippe Bloch was doing some really neat things with additive manufacturing and kind of 3D printing slabs that then are like inspired by those concepts and just laying down the material where it's needed. So hopefully, really hoping that those technologies will help bring back, that could be another avenue for making making those approaches more accessible or utilizable.
Yeah, if you don't mind me maybe
Oh,
clarifying
yeah,
that
good.
question a little bit too. I just like the Nervi slab as a structural engineer. I think the example might have actually been better for the airports that you showed. Like, I think often we find ourselves as structural engineers kind of given a design or a shape, and there can be this tension between the architect, the owner, us, around what that looks like and optimizing that. And I just would love to hear more about your experience in navigating those waters.
Yeah, I mean, just even having an architect that appreciates the, efficiency as a principle. Certainly, well, I think there's maybe a perception right now that, oh, well, a lot of materials is going to equal more cost, and your job as a structural engineer is to help us reduce costs. So, of course, you're going to design us the most materially efficient system. But actually, as you've seen, like the cost factors are not just about materials. So, yeah, I think like pointing that out, and then but yeah, we have like those opportunities to do such optimization that we had. I'd say unfortunately it is a little rare. But I'm hoping that yeah, just starting this conversation, putting it into at least like starting with a green building community, right? That making this something that enters into as a concept, and so that there is this like, you want me to design it to look like this now, like here's the penalty, and just like if we as a team like value embodied carbon and material use, then this is the trade-off. And sometimes it's justified, right? Like we have some really incredible spaces that are hard to accomplish with a more kind of traditional system and material use. But I think we have a lot of room, as you saw with like the airport example.
All right, so we have 2 minutes left, so I'm gonna ask one more question, and then it looks like there are some shorter questions in the chat that maybe we can get to. Would it help to have codes, rating systems, and other mandatory or voluntary requirements on material efficiency? So, Francis, you gave the Singapore Green Star example with the concrete usage index. So where do you all fall in terms of, would that be helpful now? If not now, when do you think we'll be ready for that? Anyone can take this one.
So the question is, could you just quickly state the question again?
Would it help to have codes, rating systems, and other mandatory or voluntary requirements on material efficiency?
So I'll just say something quick because I'd love to hear others. But I get nervous about relying on the code to tell us how to be engineers. But I understand for broad scale, probably the answer is yes. But I think we as engineers know our building the best. And if there was some other incentive to reduce it, other than it's just in the code, I think we should try to find that so that it's more of a performance-based approach on material efficiency instead of a prescriptive code-based approach.
Others want to jump in? Fraser and Francis?
Yeah, I agree. I'm actually really curious if we could take a poll of the attendees on that question. I know it's hard to send.
I don't think I'm fast enough at facilitating that on Zoom, but I do like that.
I'm also trying to respond to some of the questions in the chat.
Thanks, Fraser.
Yeah.
Well, I did see one. Mike, is there any plans to coordinate with tool developers on the taxonomy once it's ready for the world to see it? Or were they pulled in during the development process?
They were pulled in during and offered their feedback on some of these things. Our approach, as it is today on October 29th, is that we are producing what we think is best for SE2050 and the structural engineering profession, and we invite those tool organizations to adapt what we've produced. And if they have feedback or ways that can be more efficient for their workflows, that would be fine. The way we're looking at it is we're a bunch of volunteers. They're private companies that likely have more funding, and so we kind of see we'd prefer it to go that direction instead of the other way. So, if that makes sense.
Okay, well, we are a minute over, so
we are introducing a taxonomy to it'll be a simplified, like a higher level, won't be at the detailed level that Mike showed, but it'll be in the next iteration of the database and with a user guide.
That's right. Yep.
All right, well, nice way to end on highlighting SE2050 resources, which I was also going to do. And so we are recording this right now, so we will be able to share this webinar. And as well as I highly recommend looking at some of the links that were shared in the chat. There's a lot of great ones, SE2050 resources, some other ones that were highlighted. And just a huge thank you again, Francis, Fraser, and Mike. Those were fantastic presentations. I think we all learned a lot. Thanks so much.
Thank you.
everyone.
Bye.
Thank you.